Okay. Okay, you are welcome. So we quickly start. Okay, let me okay. I don't know, maybe I should just quickly explain something, the question you were asking before we now go and run. Yeah, I will do that like SK. But let's quickly look at the to revise something about the regression we did yesterday. Now, after we talk about the historical background, we said that regression is a way of predicting an outcome variable from predictor variable. That's just it. It can be one or more predictor variable. You are predicting an outcome variable from one or more predictor variable. So per time is one outcome variable you are predicting. You are not predicting more than one. You don't use regression to predict more than one. You can only predict only one variable in the regression. A type of a linear model that predicts, though it's part of the general linear model that predicts more than one. That predicts more than one is multivariate analysis. So maybe mistake. Regression is not multivariate analysis. It's multivariable analysis. Like something like multivariate analysis of variance, multidimensional scaling, factor analysis. These are multivariate analysis. Now, in regression, you predict one outcome variable. You can predict it from one predictor, which is exposure variable. That would be simple regression. If you predict it from more than one predictor variable, that's multiple regression, and that is the multivariable. It is the multiple regression that is multivariable analysis. So it can be linear or logistic. So after next week, we do the second batch of this training next week. The other week, the next 2 weeks after that one, we'll do logistic regression together with stratified analysis. So now, we now say that we can predict any data using a general equation like outcome model plus error. You create a model. You create a model with the exposure predictor. So this is the outcome. For you to predict the outcome from the predictor, you must create a model for the predictor. So that you use the predictor to create a model that will predict the outcome. Because we know that the model also will not always exactly predict everything about the outcome. Especially if you put one variable as predictor. If one variable may not be able to explain everything about that outcome variable. Then if you put two variables that are a predictor, it will explain more than one. So you add another one. So until you get able to explain, that is where the coefficient of determination comes in. As you are bringing more variables that are explaining this outcome, the proportion of the outcome you are able to explain increase. And you remember the coefficient of determination, this R square, which is regression correlation square, is the proportion of the outcome that will be accounted for by the exposure you put in to your model. So let's just move for, and whatever they cannot predict will fall under the error. So I try to bring some infographics also to add to the slide so that we can get to have more better picture. Because I discovered that when you say something, you may say, but they tend to forget. But if you see, because the brain put information in picture, if you see it, you are more likely to remember it. So we talk about the simplest description of relationship between two continuous variables is a straight line. That is, a straight line just means that how do they relate linearly? That is, no, even if you remember the correlation we discussed. It's something like that about really linear association. Okay, if this one increase, so this one increase by how many amount? If this one increase, if they move in opposite direction as one increase, the other one decrease. This one increase or this one decrease by a certain amount. That's all. And if they move in the same direction, the slope, that is, it means that if you are trying to plot y here, one vertical, one horizontal, as you are moving, as this s is increasing and y is increasing, if s increases and y increases, that should that you are, let me just take this. What I mean is that, how do you get this type of graph? It's by just, okay, maybe the value of x was here before, the value increased to this side, the value increased like this. So, and the value of y also is increasing. So as this one move from here to here, this also move. So that's you mark where they meet is the mark that you join together that become a straight line like this. So it means that as one is increasing, the other one is increasing also. That's why the slope is slant upward. But if it's the other way, as one increases, the other one decreases. Why is this, sorry. If the slope is the other way, as one increases, the other one, this second one, what will happen? It will come down. It will slope down. Now, so there are two. I will now talk about two characteristics of that type of line. The linear relationship. That is, linear line just means linear relationship. Line you just used to represent the model to represent linear relationship. So, of course, two characteristics of the line of the linear relationship is the slope. Is the slope. Look at these three things now. One, the slope is positive, it goes up. This one goes down. That's negative. Then this one is horizontal. That's like there is no slope, zero slope. If something, so it's only mean, you represent by that, mean of something. It's not slope. It's the average, like y, now the mean of y is constant, just one value. So if it is 97 under that, just draw it horizontally. If it is mean of first, you want to do whatever it is to draw it vertically. So it's only whenever it goes vertical or horizontal, there's no slope. Now, you will now see that there are two types of slope, either upward or downward. And the difference is the one that goes upward, it means that the two variables increase together. The one that slides downward means that as one increase, the other one decrease. And I said it yesterday. This is the first one now is the one that describes Sharp's law. The second one is what describes Boyle's law. Because Boyle's law is inverse relationship between volume and pressure. While Sharp's law is direct relationship between temperature and pressure. Now, we now say this is how do you measure the slope? It just the change from like this one, and look at the way it moves now. That shows that this one, what this one is just showing is that okay, you want to measure the change in x from here to here. X, this is x. X is the horizontal, y is the vertical. So from this place, S1 to S2, there's a change. You want to see the movement when the thing move from here to here. Y also move. You remember that Y also move from here to here. So Y move from Y1 to Y2 also. So we want to measure. We want to divide this change in Y over change in X. That is, can you see? That is the slope. Can you see? That's what you. So slope. The measure of this slope where you just do is this vertical, the Y. Change in Y, the Y. That is from Y1 to Y2. Change in X, the X. Remember further in differentiation, the y ds, that is just it. So the slope is change in y over change in x. So you want to know the change in y per unit change in x. And y is the outcome variable, the dependent variable, the s is independent variable. It's telling you if the independent variable x changes by 1, by how much the y change. So y is change in the slope is change in y per unit change in x. So that is the slope. The second aspect of it, of the characteristics of the line, is the intercept, where it crosses y-axis. I think that was what I was drawing yesterday. I was trying to get infographic that I didn't get better. I usually demonstrate it by drawing it, to really, you can see now from what we have done now, we have two types of slope. It's the same thing, we also have two types of intercept. Because intercept is where, let me share, where the graph cross y-axis. Y is the vertical. You all know that. If it's correlation, anyone, there's no y, there's no x. Therefore, regression, y is the vertical. This is, anything from here up is plus, plus, plus. Anything here is minus, down. This y, because this is 0. This is the positive side of y, up. The negative side. This side, right side, the positive side of x. This left side is the negative side. So the slope is about the value of x when, the value of y rather, when x is equal to 0. It's when that thing cross y-axis. It has to do with y-axis. So it can cross like this. It can cross like this. Can you see? So here, the first one, it crosses y when at the positive side. Here it crosses y down below 0. This one it crosses y above 0. Here it crosses y below 0. So the one that is above 0, the intercept is positive. The one that is below 0, the intercept is negative. So it shows you that the graph is higher when it crosses above 0. It's higher up in the geometric space, whereas it's lower up, that is below 0. The geometric space when the intercept is 0. If you remember, I did the first scenario yesterday. Well, the first scenario I did was to, if you look at this intercept positive, negative now, the slope is positive for both of them. But if the slope is negative also, you can have the same thing. In the negative slope, you can see have intercept, positive, negative. So in a negative slope now, the slope is like this. And look at it. Can you see? This is a negative slope. Here, the first one here, the intercept is positive above 0. Here, the intercept is where it crosses the y-axis is below 0. Can you see? So these are the 4 things I presented yesterday. This one here, the slope is positive, the intercept is positive. This one here, the slope is positive, the intercept is negative. This one here, the slope is negative, the intercept is positive. This one, the slope is negative, the intercept is negative. So the intercept, the slope show you the shape of the graph. Is it like this or like this? While the intercept shows the location in geometric space. Is it clear now? Is it clear?
Yes, sir. Thank you very much.
Any other question concerning that? No.
No, sir.
Okay. We'll proceed. Now, that one has explained intercept. So those are the two characteristics of the graph. And this graph, the equation you see, is actually borrowed from this is what we call equation of a straight line. When you want to write equation of a straight line, it is written like this. See, y is equal to c plus mx or ms plus c. C plus mx. C is the intercept. It is that C they got from constant. Usually, that is, it is the if you look at the intercept where it crosses y, what will be the value? The value of x will be 0 because wherever the graph will cross y, the value of x will be 0. Wherever it crosses x, the value of y will be 0. Then the intercept is about where it crosses y. So the value of corresponding x, because x is the independent variable that is determining y. So whenever x is 0, that shows that x has no value. Y still has value. That's why they call it constant. Even when x is not there, the value that is there, that's why they call it constant. So the c, the intercept, is the constant c, and the m is the slope. M is the slope, which is the change in y divided by change in x. And that is per unit change in x. So if it's 2, let's say 2, what it's telling you is that whenever x change by 1, y will change by 2. If the slope is 2, that is why y will be whatever x is multiplied by 2. That is what. So the constant is there. That is, even when x is not there, y still has something. That is, when x is 0, y has something. So I think you understand the equation now. So this equation of a straight line in mathematics is what is this here? It's not changing it. Sometimes this is not changing. So this equation of a straight line is what was adopted, the statistician adopted. So instead of calling C, the intercept C, they call it A. Then instead of calling the B, the slope, it is called B. So you now call it, instead of saying slope, so it's regression coefficient. Regression coefficient. So B slope, the y, the x. A is the intercept where it crosses the y-axis. So the regression equation I just explained now is y is equal to BO. That BO is what is a coefficient also, but it's the constant. That is the one for the constant intercept. B0, B0. The B1, S1, that is, this first one is simple linear regression. Whenever there's only one independent variable, only one x1, and we have only B1. So when you have multiple, that is, there are many more than one independent variable. So you're going to have the B0 is there, B1, X1 will be there, B2, X2 will be there, B3, X3, depending on how many, Bn, Xn. This n just means as many variable, highest number of variable you are putting in. If there are 10, that will be B10, S10. So each of them have their own regression coefficient that contribute to y. Because each of them change by 1 unit, how much will y change for each of the x? Now, this is regression equation. Then the regression model, so the difference between the equation also is part of the model, but even the model also is a form of equation anyway. But if you look at the only difference that it now had the error, because that equation will not completely predict the value of y. So whatever remains that has not predicted is the error. So look at the regression model for linear, for simple, that's single variable, simple regression. Then this for multiple. Just like what you see there, you can B1, B2, up to the highest, and error. What will happen is that as you add more variable that can explain why, the error becomes smaller and smaller. Now, this regression model, you can see, look at the way it appears on the graph. It's this same graph we talk about that, okay, the graph that has slope and intercept. But the issue is that when you plot it, not all the time, but the fact that you have line doesn't mean that all the points where independent variable and dependent variable meet, where all they meet, it doesn't mean that all of them fall on a line. There is usually a scattergram, but there will be a pattern in the sense that if they are increasing or decreasing, there will be a pattern. And if it doesn't have a pattern, it may not likely predict it at all. It will scatter. If you see graph that scatter like that, it's not likely to predict. But if you see, you know it's scatter better, you see I'm moving along the line, either it's going down or going up. You know, it's more likely to predict it because you see that it's increasing, there's a pattern. So now each of these dots are the data point where the value of, maybe if the value of x is here now, where y is here, where they meet is that dot. So now the line, the regression line, which is the model, which is the model formed by the, explained by the x independent variable, is the line. Now the error now, whatever remains that the line cannot explain, is what the distance between the line and each point. Now, we now see if we are to obtain the line, how do we obtain that line? If we are to give you this, if you look at that, one is scatter more than the other, but let's say we give these two to you, each person. Come and help us draw the line. You will not draw the same line because you are trying to, all of them, they are not in a straight line. You just draw line, everybody will draw slightly different line. So now, how do we know the best line? The best line will be the line of best fit, the one that fits best. How do we get the line that fits best? How do we know which one fits best? But from the intelligent people, the way they work is that if you draw the line and you try to now look at the distance between each point to the line, the difference in the distance will be the error. The difference, those ones that are below the line, negative. The error, that is the value is less than the, it's not up to what they predict for them. So one thing I want you to see here is that look at this graph. Look at, for example, this. Let me bring this. Look at for this dot now. So this thing, where if you draw a line from that dot to join the regression line, that point is that is what the regression model predicts for that point, for the value. But observe value, the one you observe, the value you have in your study is this one you are showing on this dot. But this is what the model predicted for it. So there's a distance. Can you see the error now is the distance, the difference between the predicted and the observed. That is the error. Now, the best line will be a line that if you now calculate the error and for all of them and square it, if let's say 5 of you draw different line now, we now calculate the error from each point to the line you draw and square it. Depending on how the small level, when you square and add everything together, the person that has the smallest one will be the best line, because it will be the line, that is the method of least square. That is the one that gives us the least square. When you sum all the square together, it gives us the smallest. That is, averagely is the one that is closest, that draw a line that make all the point to be closest to the line. That is the best line. So the line of best fit is gotten through method of least square. I don't know if there's any question concerning that. Because this is the logic. Once you understand the logic behind it, that's just the logic. Yes? Yes?
Okay, sir. Thank you very much, sir. This is very clear. But I wanted to just ask, just to confirm again. So what you were saying was that the observed value is the one that is above the line. That is what you see in your data.
dots,
but
dots.
That predicted one is the one when you now draw that line.
Yeah, it's where the thing
so
will
then,
make the line.
What I wanted to just confirm was that you said that yes. So what I wanted to confirm is,
I can't hear you.
So what I wanted to confirm is how you got. Hello, can you hear me, sir?
I can hear you. I can hear you. I can hear you. I'm hearing you.
Okay. What I wanted. Okay, sir. What I wanted to ask is this least squares. There was a way you explained it. You said when you square that error, the one is it the one that is the least value? That means each of these y. So you take each dot and you do a y. You do a difference in their y. Then it's the one that has the smallest. Is it the one that is the one that has the okay?
No. When you do for all of them, you will not add it together.
Okay.
What we are saying is that if, let's say, we draw many lines now, if you are to draw this line now, there are many lines you can draw for this thing, because all of them, because since they are not on the straight line, you can draw different lines. If, let's say, you draw about 10 different lines now, if you now, for each of the line, you look at the distance between each point and the line and square it and add everything together. The line, the one that gives you the smallest value would be the best. That's what we call method of least square. Least square, we are talking about when you square, you add everything together. Because some of them are negative. All these ones that are below the line, they are negative now. The ones that are above the line, they are positive. So if you add them together like that, it will give you 0. Because normally, most of the time, it will give you 0. But so, in mathematics, what you do is that you square it. It's the same logic we have been using when you are calculating variance. X minus X bar, square, sum of square. That's what we have been talking about now, sum of square. Right? That is when you square the difference between a point and this thing. If you are talking of mean now, when you remove each mean from each value, you sum it. You square it and sum it. That's sum of square. It's the same thing. This is sum of.
So that means the lowest that you. So that means the lowest that you eventually get will now be the one that will give you the best line of fit.
Exactly, the line you draw that give you when you do the sum of square, that give you the smallest. That's so that is the one that really makes all the points to be closest to the line. Yes. That is
Thank you very much.
That would be the line of best fit, and the method is method of least square to get the line of best fit. Is it clear now?
Thank you.
We move forward.
Yes, sir. Thank you.
Now.
Yes, sir.
Now, the line, look at it. So what it's just telling you is that if you look at the error we have just explained, the line, so the slope of this graph is, B1. This one is for simple linear regression now, one model. So you can now see that the slope, B1, that the difference, the change in the change in, what do I call it, in Y per unit change in X. Let's say from here to here is a unit change in X. The change in Y would be B1, which is the slope. Y, BO, can you see this BO here is the intercept the value of Y when S is equal to 0, where the graph cross Y axis. It just explaining what I've said before. Hello? Then we now say that after talking about that, okay, I think sorry, what we have done. Yeah, let me change this. Yes, change that slide. So what I've just explained now is what you can see graphically. You see these three graphs you see here. It's the same graph we have just shown now, but the one that is showing the regression line, this second one. You know, if you look at it, what you join together, the difference between the predicted and the observed is the error. You get, so is the error. So that sum of square, we say that method of least square, that sum of square we get there is actually sum of square of the error, that is different between the line and the each value. Now, we want to see, after we have plotted this graph now, though we can easily calculate our regression coefficient B1 and then B0, but before you can say the result is valid, it makes sense. You want to see measure of goodness of fit. If you want to fit, how do you measure the goodness of fit for this graph? Does it graph, is it okay? Does it fit? Does it predict it very well? That is what we want to look at here. Now, for you to be able to do that, one of the things you do is what we call analysis of variance. And that's what you see yesterday. That was when we talk about the analysis of variance and regression is a component part of regression. So we say analysis of variance and regression, and you help me on this. It's the same. They are the same. Now, if you remember our analysis of variance, we did ANOVA. We talked about 3 levels of variances, if you remember. Variance between, variance within, and total variance. Total variance is the one that explains the whole variance in the data set. Go and check if that bucket is the thing dropping on that bucket. Then when the variance between is the one that divides the group, the difference between the group. Then variance within in ANOVA is the difference between each mean. There is that thing inside. So now, what you now do is to correlate. Let's see how that ANOVA work with this. The total variance here is the difference from each point and the mean. Because if we want to know this regression line, does it fit very well? What standard will you use? There's no other standard. The only standard you can have is the mean. Is the mean that you can, okay, is the crudest model. It's a model on its own. And the mean, its own is that all animals are equal. The mean value is the whole total value divided by the number. So equal for everyone. That's why we say that the mean is the value, is an expected value. Is the value when no hypothesis is true. Imagine now, as we are here now, yeah, all of us in this class now, somebody say he had all our age together and divide by the number and now say this is the average age. He's assuming that, okay, he's collecting all the age together and divide it. It's like as if you collect everybody's money from everybody, not divide it equally among people. We all of you should have the same amount. That's what the mean means. Somebody say average age is this. He tries to give you equal value to everybody. I don't know if you understand. So it's the crudest model, it's a model. So if you look at the line, horizontal line in the first graph here, is representing the mean of y. No, y is on the vertical axis. So the mean of y. If you look at the point of each value from the mean, averagely is farther compared with that of regression line. And you see a lot of them, though some are close, a lot of them are far. So if you now want to know the total variance, all you need to do is you remove each observed value from the value predicted by the mean. Just like the way we look for the regression line. If you do that and square it, the sum of square, the total sum of square will measure the total variance for us. Then the model's own, we have already understood that it is different between what the regression line predicted and the observed value. So the difference is the error. That is the error, the regression line now made in prediction. But you can see that, to be sincere with you, even with that error still, the regression line is closer to each value than the mean. So because the total variance you're going to see in the set is represented by the mean. Now, for you to really know the improvement made by the model, we know that the total variance is explained by the crudest model. That is the worst model, which is the mean. Then you now have a regression model, which say has improved it, but we don't know. For us to know how much it has improved, we are using the mean, the standard, the crudest model as the basis. What you now do is that by how much is it better? What is the difference now? So what is the difference? The total variance to be explained is the mean. Let's say the mean project the total problem to be solved. The error here now is the one unsolved. So to really know how many of the problem have been solved is to remove this error from the total variance to really know what has been solved. So when you look at it now, the sum of square total minus sum of square residual give you the sum of square model. In other way, if you add sum of square model to the residual, it gives you the total sum of square. Just as in the ANOVA, when you add sum of square between and sum of square within, it gives you total sum of square. So what the total sum of what corresponds to the total sum of square in ANOVA, in this one in ANOVA, and this one is the total sum of square in ANOVA, and this total sum of square presented by the mean here. So in ANOVA it's the same thing also, because the total sum of square gotten by removing each grand mean, the total overall mean from each value. That's what gives you this total variance. And it's the same thing here. You are removing the mean. This is the mean from each value. It gives you total sum of square. So now the sum of square residual corresponds to the sum of square within in ANOVA. The sum of square residual here is the one that corresponds to the sum of square within, which is in ANOVA the difference between each group mean and the value, each value and their group mean. Now, what corresponds to the sum of square model here in ANOVA is the sum of square between, which tell you the difference between the mean of each group and the grand mean. So it's only that in calculating this one, you remove the residual from this. If you look at the same thing also, because when you add the residual sum of square and model sum of square, it gives you total sum of square. Just like the way you have within and between in ANOVA give you total. So look at this total and say sum of squares total SST uses the difference between the observed data and the mean value of y, while SSR, sum of square residual, uses the difference between the observed data and the regression line. And SSM, sum of square model, uses the difference between the mean value of y and the regression line. So I think it's clear. Is there any question concerning this one? Any question? It's clear, okay. Now, if you look at it now, the two to measure the goodness of it now, I explained yesterday, those two things is from this variance you calculate. R square. R square, this, if you put this total sum of square model, which is the one that this variance that can be explained by the model divided by the total, that would be the R square. The sum of square explained by the model, what the model can be explained, and the total thing to be explained. That is why the R square to tell you the percentage change in the outcome variable, which is the Y, which can be explained by the X, which is the predictor variable, independent variable, which form the model, which you use to set up the model. Can you see now? So what model can explain now is what your what part of the outcome variable the exposure variable can explain. So the sum of square model over total sum of square, and that is what they call the R square. Because you can get it two way. You get it through this way, or you even correlation, you square the correlation they give you. That's why they call it R square. And it is called coefficient of determination. Now, the second one is the F ratio. We are used to that one because the F ratio, what it does is to look at the variance between in and over divided by the variance within. What is saying that what the variance between E and I is the model. What the model can explain and the error it cannot explain. If what you can explain, you divide it as numerator, you divide it by the what you cannot explain, which is your error. And if it is more than one, that is, it shows that what you can explain is far, far greater than what you cannot explain. So like when we run it yesterday, around about 32 times, it's telling you that what the model can explain is 32 times what the model cannot explain. Is it not good enough? So that is why these two statistics are the two measures of the goodness of faith. It is when they are robust, you can now say, okay, whatever, you go ahead and calculate your B2 and B1 and the slope and this thing, and now make conclusion. And now make use of it. Are we together? Now, yesterday I explained this. What is wrong with this thing? I just want to throw more light. The regression equal the B, how do you calculate it? Apart from plotting a graph and just how do you mathematically? You remember, how did we calculate the regression correlation coefficient? With a correlation is a standardized covariance. That is, correlation between X and Y is when you calculate the covariance between X and Y and divide by the standard deviation of X and Y, it gives you correlation. But the regression, that's correlation coefficient. The regression coefficient is not too far from that also. The same covariance. The regression coefficient between X and Y, of course, the regression coefficient that is change in Y by unit change in X is covariance of both of them divided by the variance of X. You know, it says change in Y per unit change in X. So actually, the change in Y you observe is the change in Y that it has together with X, and that is the covariance. So change in Y per unit change in X will now mean the covariance over variance of X. Can you see that? Change in Y per unit change in X will be because when you are talking of change in Y due to X is the covariance of them, that is when both of them change together, divided by the variance of X. And that is why look at it, the formula for covariance over the formula for variance of X. If you look at it, this divided by this. If you change subject or formula, no, you change this one times. This n minus 1 become numerator, this one, numerator become denominator. This n minus 1 cancel n minus 1, it now become this. Can you see that? This is the formula for regression coefficient. It can be written like this one. And the data we were giving that we use No, we calculated, if you look at it, the data, if you look at the data, we calculated what we calculated. If you look at it, the x minus s bar, y minus y bar, which is the numerator now, then that is the covariance aspect of it. Then when you actually the denominator, x minus s square, s bar square, without the square root, which is 5251.6. So 5426.6 divided by 5251.6. Sorry, that is the, you see, that is our regression. And for you to now, after you are calculated, for you to calculate your A, which is the constant, all you need to do is to apply the formula. If you y A, you know y is equal to A plus BS. You can as well say that the mean of y is equal to A plus B mean of x by x. So if you change the subject of formula, you will be able to say A is equal to by y minus B by x. By x and by y, we already know that they are the mean of x and mean of y. So mean of y, mean of x, with the coefficient there, b, you'll be able to get A. So you can now write the equation, regression equation of y on x will be y is equal to minus 82.4 plus 1033x. So if you want to try it now, let's even try it. Let's somebody write the equation because it's workshop. Let somebody write the equation now. Please copy the equation. This last one, that red one. And I want you to copy it somewhere. Now, well, I want us to solve it. I want you to quickly solve it. For one, we are going to pick one of those, the value for the original value to see. So have you copied it? Just write it somewhere. Have you written it? Now, let's check this number one. Let's look at number one, where the height is 110. It's the same data set you used to do it. The height, the pulmonary dead space is 44. So let's put in, instead of let's write the equation and write the height there now. And let's calculate y. So height is the x now, minus 82.4 plus 1.033 times 110. Let's solve it. What is the answer? So whatever if you have gotten it, let me know.
I got 31.23. I don't know if that's correct.
31.2, right?
So, yes, sir.
Yeah.
Is it correct?
No, I don't know. I don't know if it's correct, but I just want to know that let other people confirm. Let another person confirm, and let another person confirm what you got. If it's the same. Nobody has got him. Me, I got 31.23.
Oh, hey, that's what I got. I got 31.23.
Yes.
So, sir, does that mean, so that's 31.23, which is equal to what?
That is the for that height that the person is 110 centimeter now. It has predicted the pulmonary something to be 31.23.
31.23.
Yeah, thank you, sir. So, and usually look at the value that is there for pulmonary death space for that species is 44.
It's 44.
So the difference is the error. That's what
error. Thank you, sir.
So the difference, the error in the model now is 12.77. I don't know.
Thank you.
You get it now?
Yes, sir. Wow.
So 12.77, that is the error. So, you know, when you form the model, so if you look at it, we already, we discovered yesterday that it only accounts for about 71%. So it cannot predict everything. It cannot, so it can only explain 71%. So it cannot predict everything. I don't know if you understand me now.
Yes, sir. Yes, sir.
And if
Yes,
you
sir, you are.
please, just try put 31.23 over 44. You're going to see that it gives you around 71%. 23 over 44. If you remember, our arrow square when we run it is 71% when we arrow square. If you look at it, 31.23 over 44 is 71. Can you see?
71, yes.
Yeah. So it can only predict about 71%. It accounts for 5. So if let's say we do more literature review and we can locate other variable that can explain the remaining one. So if you now merge it together, it can give you up to 90-something%. If you give you up to 90%, so with those two variable or three variable, you'll be able to explain close to the answer. Does it make sense now?
Yes, sir. Yes, sir.
That is, can you see the way the regression work? So now, before we will going to today now we run that one again and we now do multiple regression. Let's quickly talk about this multiple. Whereas the multiple is when you have more than one variable involved. Now, more than one predictor. Now, there are methods of running this multiple regression. No, we have hierarchical block entry, first entry, stepwise method. Though it's the same stepwise method that you have two types, forward or backward. Under the forward method, okay, when we say hierarchical method, if you want to run it, is selected based on past and experiment, maybe experimental design in which way to enter the predictor. Maybe you have done some literature review or some you have read something. These are the factor, the first factor. So if that's one guide, or that's hierarchical method. Then we have first entry. First entry, just put all the variables there. That is first entry. That's what we did for your first entry. Then you have stepwise method. That stepwise method can be backward or forward. So in backward, bringing everything forward, put one and begin to see which one. You first of all do. That's why you do simple regression for each of them, for all the variable. You want to have the best this thing, you now begin to add. You should want to have the best coefficient of determination. You now add in the next one. You need to move forward until there's no more improvement in that thing. We'll do it, don't worry. Then in backward, you put everything, you are now removing. So people believe that the backward is far important, better than the forward, because they say that there is something called suppression effect. That suppression effect, there are some until you hold some variable constant, some variable alpha association, they will not express themselves. They will not express unless you hold the other one constant. So that suppression effect is usually commoner with backward and forward. So that's why some people prefer forward. Now, the assumption you have to make in using multiple regression. All predictor variables must be quantitative or categorical with two categories. Can you see now? That is, the predictor variable quantitative. If you are using categorical, that is logic behind producing dummy, creating dummy. The dummy, what a regression does is to create two categories, give that impression of that two categories, 0, 1, 0, 1. Then non-zero variance, the predictor should have some variation in value. So any predictor that doesn't is the same. It's just like you want to do regression now. Maybe male and female. All of them are male. It doesn't matter. It doesn't make sense. Or maybe it's diabetic, not diabetic, obese, not obese. And all of them are obese. It's rubbish because there's no variation. All of them have the same value. So you cannot use it. Doesn't make sense. No perfect multicollinearity. What they call multicollinearity is that there are sometimes two variables, they will correlate 100% or true. The correlation will be 1. I've encountered that type in multiple research. But if you put both of them in, it's only one that will run there. Because both of them is the same correlate, the same thing. They are serving as the same thing. So that is multicollinearity. When you have some variables that have the same, they perfectly correlate. That their correlation is almost 1 or 1. That's perfect collinearity, multicollinearity. No, you should not use that type of thing. Predictors are correlated with external variable. So there should be no external variable that correlates with any of the variables included in the regression model. External variables are variables that have not been included in the regression model, which influence the outcome variable. So there are some external variable. Maybe there's a factor. Yeah, thank you, sir. On founder, he relate to the outcome and it correlates also with the YAN output. So if you have brought the other one, you may cancel the effect of this one. So that is why when you are doing a study, you have not done extensive literature review to include all the possible confounder, your result will go to, that's why extensive literature review and to establish many factors that may be responsible is part of the research. If you don't do that, you are going to have a result that is erroneous. There's one person now that O&G that just analyzed his part 2, and the way he designed his work, the design was not so good, but it was accepted by the people that assess it. But one of the assessors also was not saying you should do regression, logistic regression. But now the way his structure is, even if they want somebody to do it, he will have, maybe he didn't understand. I don't even know when they even said, I think before, okay, I think that was the comment. However, the person can proceed and just make all this correction. But the person doesn't know, he didn't understand, he just proceeded. So if he has to, in the objective, he's not talking about any factor, why does he want to do the regression? So some of those factors will have even done regression, we didn't include them. So now he just want to do the regression so that at least for him to pass. Can you see? That type of work. If they publish it now and they are telling lie with statistics unknowingly, no, you can tell lie without knowing. So they are telling lie with statistics. And you now read that type of thing you want to use to take decision. It's at your own risk. Now, more perfect, okay, I think I have talked about all this. Then, okay, I guess no perfect colonization, predictor unrelated. Then homoscedasticity. You know, this one is like when we say homogeneity of variant. The homoscedasticity means each level of predictor variable, the variance of the residual time should be constant. What it's just saying is that just like the way when you are trying to do parametric tests, the variance must not differ of different groups. Must not differ. That which is homogeneity of variance. This one now is the variance of the residual. It's called homoscedasticity. It's just the same thing, almost the same thing as the other one. So the independent errors, for any two observations, the residual time should be uncorrelated. That is, the residual time should be uncorrelated. Any two observations, that is, what he's saying is that for each person, different people that for a subject, their error should not correlate. Well, there are different ways to say that those one. That's what they call auto correlation. No, those people in this thing, they do it a lot. Econometric, because they usually have variable that the error auto correlates. So they call it autocorrelation. And the way to test is what the Watson test. Leave that one. Normally distributed error. This assumes that the residual in the model are random and should be normally distributed with mean of 0. Independent, this assumes that all the values of the outcome variable are independent. Well, the same assumption is true for using any parametric test. Linearity, this implies that the mean of the outcome variable for each increment of the line in a straight line. Believe that there's a linear relationship. So this multicollinearity we have talked about, I think I have talked about it. When you are having one or two variables that are perfectly correlated. If you do their correlation, one perfectly, you cannot put them, both of them as you cannot run both of them. You cannot put both of them inside. So I think let's quickly go on the practical. Some of these things you get to understand them as I'll be explaining as we are running. We have a lot of data set to run, so to run it. But I don't know if there's any question before we start running it now. We first start with what we did yesterday. The one we run yesterday, we quickly run it. Then we proceed. Any question? No question.
Yeah. Hello.
Yes, sir. Go on, sir.
Yeah.
Go on.
I'm just wondering. The assumptions are quite numerous.
Yes.
And
yes.
One can imagine that before you can make valid conclusions, it means that your data must meet the assumptions. Then does it mean one has to test these almost 10 assumptions before you determine that it is appropriate to use this type of analysis, just as in the others, the testing for parametric, for example? There are so many things to test to make sure that, yes, this data set has met all the assumptions, so I'm free to go ahead and use this type of analysis.
Actually, they look like that, but sometimes in real life, theory is different from practical. Some of them, they even need tests. Some of them, you just know. And you cannot, all those conditions cannot come up in all situations. So what actually happens is that there's only few of them that even come up in your own situation, if any. So it's not even possible for all of them to even come up. Yes, I mean, it's not like this autocorrelation now. W. Johnson, there's a test for it. So it's just even as you are running, those, they have already input some of those even assumptions. They're just like when you want to do your t-test, the homogeneity of variance is every test along the way. It's the same thing here. So even when you are doing your multiple regression, you get to like multiple collinear, you yourself, you know. And that is why also when you are dealing with this quantitative variable, you first of all do correlation. When you do correlation table, you know those who correlate very well. If there's going to be multicollinearity. And you see now, you get to the screening. So it comes by experience anyway. It's come by experience. It's just like when your student asks you some question, all these things, how do you get to marry everything together? You say by experience. So it works together. Don't worry, it's not a big deal. It's just a matter of understanding it and go ahead. Yes, somebody say what about unbonded? Yes, thank you. Unbonded means that when there's no limit. It's just like if somebody say, okay, you are measuring something on a scale of 1 to 10 now. It's bonded. A scale of 1 to 10, even in between, that is where that problem comes in. Like if we say something like all this Likert scale, that 1, 2, 3, 4, even if it's up to 10 or up to 5. No, we already said it. Sometimes you can use some parametric test if you have already calculated the mean of the domain. But in this case, Even if you do it now, it's bonded, because if you have put something on a Likert scale of 1 to 5, if you now calculate the average for a particular, maybe 5 or 10 of them that make up a domain, introduce decimal, there is still bonded in the sense that it cannot be greater than 1, in less than 1, it cannot be greater than 5. It's bonded. You get it now? So when it means unbonded, it should be something that is free. So even in real life also, when you say something unbonded, there's something don't, you have outliers, like age now. Age is not bounded, but we know that the population, when you study people, there is limit to the age also. So the unbounded one just means that it means that it's not actually appropriate for all those Likert scale data where you have limited. Even if you introduce decimal inside, it's still the upper limit, the lower limit, so it's narrow, it's bounded. Okay. Any other one? Okay, let's Dr. Odusholu. Dr. Odusholu. Yes. Yeah, would you have your
Good evening, sir.
Okay, good evening. Have I even share your data with you, the last one? Have I share with you because
No, sir.
Because I won't ask you to run what you have because I don't know the type of thing you. So somebody asked a question. I want to run your data for it because we did something yesterday. Say they are looking for Likert. I say all your work is about Likert scale. In fact, you use about to, if not to 5 Likert scale that you use. You have this. You have quality of perception of this, by smelling of this, hearing of this. All of them, they are on a scale of 1 to 5, different scale. So I say your data is a perfect one for it. So I want to just open your data now. It's only me that will open it.
Okay, sir.
We just run we just run what do I call it? Schema, because it's already on Likert scale there. Yes. I want to quickly do that one before we proceed. Somebody should be prepared to share this thing. What we did yesterday, pulmonary height and pulmonary something, so that we proceed. Let me first of all share our own first.
Dead space.
Yes, pulmonary dead space. Let me just first of all share our own data first.
People are not responding.
People are not responding. No, it's me that we share first. It's me that we share first. I'm coming. I want to share something first.
Okay.
Yes, I want to share something first.
That guy's data.
Yes. So can you see the data set? Can you see the data set?
Oh, yes, it's come up, yes.
So I want to, Professor Tokiden. Prof. Is it there?
Yes, we can.
Yes, Professor Tokiden.
Yes, sir.
Yes, what I just want to show you is that this lady's data, quality of life, you will see, if I open, you see the, you see, they are all Likert scale. Can you see? Can you see? 1 to 5. Most of the data set. No, all the not
yes,
at all.
sir.
A little, a moderate,
not at all,
very much,
little,
and extreme. This is just one of them. There are plenty like that. There's another one here. Very dissatisfied, neither satisfied, very. That is what she did. You see another set all the time, usually, sometimes. So it does not finish. You see some, never really. There's some other scale. This one is strongly agree, disagree, not sure,
Sometimes
agree.
mean nearly always, always.
The same
It's
thing
like
with
social
this one.
sciences.
You know, he has many skills he work with here. Now, I just want to pick some of them and just do the, which number did I pick? Let me just pick some in this number 17 to, and just do correlate. Okay. Let me just pick some. Analyze. Correlate. Bivariate. Let me just start from here.
Diagnostic.
Let me just pick only 5 and correlate. So let me put by default, Pearson is there, Kendall is there, Spearman. Let me just remove Kendall. Let me just get Spearman. Okay, let me just pick 3.
So isn't it?
Let me share the results. Can you see the result now? Can you see the results? Can you see the results? Nobody is answering. Can we see the results? Oh my God, this thing, the network has gone. Ayo, if you say, which one are you using? Which network are you using? Okay. Can you hear me? Okay. Can you hear me? Can somebody hear?
Yes, sir.
But
Yes,
yes,
sir.
Yes, okay. Look at the results. This one is first of all showed.
Yes, it's come.
No, there are, okay, no, this is the one I've done before, sorry. Look at the results. How will you rate? No, look at the correlation. So the same question 15, 16, 17, 18, 19. In 19, I didn't give horizontally also. So the horizontal one are the concordant. Off the line are the discordant. Those are the one of the diagonal are the discordant. Those are the one you are using. Can you see these are the
I just noticed something.
Yes.
That's the between the Q17 and the Q18.
Mm-hmm.
The correlation 1.000.
One, that's perfect now.
Okay. Thank you.
16 and 7. 6. You say between what and what, sir? Let me.
17 and 18.
Okay.
That's 17. Yes.
I'm trying to look at it. 17
Can
correlate.
you see 17? Then look at 18.
17 correlate with 18. 17. What does it correlate with 18?
Here.
Like question 18 on the fourth.
18,
on the fourth column.
Yes, it's perfect. That's
Okay.
example of what correlation. Multicollinearity.
Okay, see the same
What they call multicollinearity. When
yes, but that's what I was going to ask.
Yes, no. So if you want to, maybe you want to use them as for multiple regression, you cannot use both of them. Yes, I mean now. In fact, if you even feed both of them in, only one will run. You will not see the other one because it's the same. That's multicollinearity. Okay, this is Pearson. Look at the Spearman and Kendall. Kendall and Spearman. Look at Spearman. Check the same thing because Spearman is actually smaller than Kendall is actually smaller. Spearman. Let's check that 17, 18 now. It is
we're not seeing the.
We're not seeing the heading.
Okay. You know
the upper questions.
And the reason is that let me go on because it put we did both candle. Let me go and redo it. We did both candle, so it puts too much things there. If you usually put candle and sperma in the same table. Yes, I mean now. Let me redo it and do only. Let me redo
The
it.
candle is there.
Candle is there, the sperma. Okay. Okay, just look at the candle anyway. No problem.
Candle is there. Candle is there. Yeah, it's there. It's there.
Yes.
Yeah, the candle is there.
That's
It's
16
also
and
the
8.
same thing in Kendall too. Yeah.
17, 18, yeah.
Is
It's
it one also?
It's perfect. Yeah,
Yes, sir.
it's perfect.
Okay,
It's perfect.
Okay. Yeah. I'm sure it will be the same thing for sperma. Same thing. Look at it. No, hope is not the diagonal you are looking at. Hope is not the diagonal. Wait. Let me even go and see. Okay, it's not the diagonal
Okay, so
because
look
it's not
at
the diagonal.
17.
Yes,
Yes, look at
it's
18.
the
It's
diagonal.
not.
Yeah, it's true. It's not the diagonal. Okay, I think we can proceed. Let me just.
Yeah.
The sperm is the same.
So somebody should share the yesterday.
Pulmonary dead space.
Yes, let's quickly do it.
Pulmonary dead space.
Height and
It's
pulmonary.
like everybody's here today.
What do you say?
I say it looks like everybody is ready to share today.
Okay.
Go ahead with your pulmonary dead space. Not the living space, but the dead one.
No, the meaning of dead space doesn't mean actually it means that of course.
Professor Wakwe. Ogini.
Everything that is dead now. That means the pulmonary is no more living.
Okay, okay, let me allow share.
You disabled screen sharing, sir.
And that's what I want to do, sorry. So I've enabled it.
Oh, I thought it's Jenny sharing.
Okay, I see Ugo sharing too.
No problem, you share
So
another
Jen, you can stop.
Okay.
Yeah.
So let's go and run what we did yesterday. Okay. They say Jane should share. Okay. Let's do what we did yesterday so that we play.
Jane, you can share since I've shared before.
Okay.
Jane,
It's the same thing.
Even if you share, I will still learn from you.
But you know, there's nothing as good as practicing it. That's when you're the one doing it. You remember it more. I don't want to
you are speaking, Prof. The person you are speaking to is Indigbo. He doesn't understand Yoruba, even though he's in Lagos. He doesn't understand Yoruba. Is Indigbo? Yes, now Ugo. He's speaking Yoruba.
No, I hear Yoruba now. Don't you didn't know?
I don't know. Okay.
Yes. Oh,
okay,
no, I hear Yoruba.
So now because your mom has been in Lagos for long now, yes.
Yes, I grew up here. I was born in Ife. So.
I know your mom is a prof in pharmacology or pharmacy.
Yes, sir, pharmacy.
Pharmacy.
In pharmacy, yes, sir.
I know. Oh, that's great.
Thank you, sir.
But you escaped. You didn't marry Yoruba. You escaped to somebody. They sent somebody from the village to harvest you.
There was no correlation then.
There was no correlation.
Andrew, then you.
Who is sharing?
It's a Jane.
It's Jane.
Okay, if it's not, share your own. Jane will share another one. Please share. Let's.
Okay.
Share that one. Jane will share another one. But let's just share this and proceed.
Okay. Just the one you can see it.
Okay, let's know the next one to be shared so we can open it and keep.
Yes,
don't worry.
Death rate.
Death
rate. Death rate.
Now.
Even this bed. It's like Prof also live in Lagos.
Yes, I'm telling you.
Okay, let's continue. Okay. You go to
regression.
Regression. No,
Okay.
yesterday we did the correlation. We don't need to go. Yes, the regression. Just go to regression. Go
Linear.
linear. So dependent is pulmonary test rate. Yes. Independent is Independent is height. That's it. Just click OK. So share the result now. You have to.
So can you see it?
It's coming up.
Not yet. It's still coming.
Okay.
Yes. That's come.
It has arrived.
Yes. We explained this thing yesterday. You need to go over everything because it was the last one that the thing started misbehaving.
Yeah. It's the third
go over
one.
everything, okay? Now.
No, we just go to that third one, but we spent so much time in the first two. The third one.
Okay. Is it? We all
The
agree with that.
coefficient.
Do you all agree with that? If you have something that's not clear, ask so, please. Okay. All these things, if you look at
coefficients.
Okay, the coefficient.
That's where we stopped.
I said we discussed the model summary and ANOVA extensively yesterday.
Okay, that's great. Now that's great. So if you look at it now, you will see that the B, you will see B.
Unstandardized.
Yes, you will see. I'm checking off. Well, I don't know. You will see this B. Can you see the B? That is the B, the coefficient, regression coefficient. What is this? Look at this nonsense.
Minus.
I was actually looking for, okay. Okay, that B, can you see? That is the regression coefficient. But you will see that on that table, you see model constant. That constant is the A, you remember, is the A, that's the intercept. So that BO is that first one. If you remember, what we get is minus 82.5 or 4. Can you see? You don't know what you got?
Okay, that first one is the A.
Is the A.
Is the BO. Is the BO.
BO, yes, is the BO. That is 82.4.
Yes, that's what we got.
And minus, you can see minus 82.4, yes. Now, you will not see the next one. You will not see the meter, height in meter. That is the, because it's simple regression. It's only one variable.
Just one variable.
Yeah, only one exposure variable. So if you see the regression, is it not 1.033 we got? The answer. As the regression for your Q1. Exactly. Can you see? So you will see their standard error. You now see you see a standardized coefficient. That standardized coefficient is 0.846. That one is parameter. Why this one this here is what do I call it? Is this one is the statistic, but in the population, that standardized one is the parameter. Now, you will see that there's a significant here, there's a T test. You know, this T test is also what you use to test for the correlation between them, right? So, but the most important thing here, most of the time, even the significant here is not, it doesn't make sense. The most important thing is that arrow square. Once I see that thing is fit very well, the goodness of it. So I can be confident that I will be able to predict the value up to 71%. Are we following? We have already done it. We did it. when we went to put, we pick one of those values now, we apply the formula into it, because the formula now, once you get your B here, A is here, you can write the formula, the regression equation out. If you now go and apply it to one of the data set, one of the subject, to really see, you will see that that percentage of the R square is to that extent that it will predict the value of Y.
It will be about that.
Yes. Imagine if you now do it and your this is not even up to 10, around 10%, or not even up to 20%, and somebody is making recommendation, and it can be significant. Even the ANOVA can be significant. But to me, does it make sense? Does it make sense? And that was what I realized this work even is in the University of National State University. They did the study to really know how to improve. What are the factors that they say maybe it improve student performance or whatever. So they now did it. Now listed they did the regression. Then when I was seeing the results, the public they gave the recommendation, I just look straight to the result. The coefficient of dimension not up to 20%. So I mean, what type of recommendation is that? That shows that there are a lot of factors that they didn't even study that it must be responsible for about 87% that they have not accounted for, and they are giving recommendation. Instead of them to go and do extensive detail, what are those factors, and go and redo the study to really know. So if they make any recommendation based on that, take any decision that they are wasted, they will not see improvement. And those are the problems someone like what do I call it, Disraeli faced as Prime Minister of UK. You see, there are three kinds of lies: damn lies, and statistics. So they will tell that this study has been done, it will improve this, and they will channel resources. It will go into thin air, and nothing will improve because of all these problems. So I think now let somebody share. You can stop sharing and let somebody share pulmonary death space. To share death rate. Because that one.
Okay, you have moved.
Okay, you want to ask a question? You have a question?
Yes.
Oh, sorry.
Okay,
I wanted to ask. Okay, let me share it
Can you
again.
go back?
Go back. Yeah,
go back to the output.
Can you see it now, sir?
It's still coming.
We have not seen anything. Okay. It has not even started coming.
It's come out.
From what you have explained.
Yes, go on.
Now I can see from here.
Okay.
From what you have explained concerning this regression coefficient,
yes.
Since coefficient,
okay.
Can you hear me?
Okay, go on, sir.
Looks like
I can hear you. Go on. What did you say?
I said that at the end of the day, after your analysis,
yes,
what you are going to rely on is the R square. And
yes.
even if it is low, say 20%, you are going to use it for your inference to say that what they did is not very suitable, depending on how the person concludes.
So
if it is like that, then what is the relevance of this
regression coefficient?
Oh, that is what are you saying? Just like the R square is to see if this thing is worth it, is fit. When it is worth it, what you are going to use is that one. It's just like when we say somebody brought a car for you. You first of all test if the car is worth it. No, it will do what it's supposed to do. You understand me now? So if they not say, oh, the car will do what it's supposed to do for you, maybe they bought you a Range Rover or he lost to go and do, we want to do farming, it will do it. Now, this thing now is the functioning of the car. How do you now use the car? So the B square, and this is the usage, the regression coefficient is the rule usage. Let me give example now. Let's say in the report, you are a gynecologist now, you are in a resource poor setting, and there's a particular, maybe ultrasound. You need to do some ultrasound to know the weight of the baby, to know the gestational year, all those, to assess something. And in that place, there's no ultrasound. Maybe Doppler, there's no ultrasound. And there's some other thing you can now do to see. So if you now try to regress, to correlate both of them and do regression, can this thing predict the ultrasound? So the outcome measure you are now looking at is the, maybe you say the fetal weight, and you are now using something apart from using ultrasound to predict the fetal weight, or maybe the hair circumference, or whatever you usually do, or the fetal, the age of the baby, to predict. So by the time they now do it, they now say the predict the R square is less than 10%. Just forget. But if they say the R square is 80, 90 something percent, you are not happy that it's free. So now what you now, you measure maybe tummy height. You know that if the tummy change in fetal height,
Fundal height, yeah.
Fundal height. So by the time you now say, okay, the regression coefficient is this.
If fundal height is
yes,
also
once
so,
you get your fundal height, which is X, you'll get your the child's weight, which is your Y. I don't know if you understand me now. So that's the essence. You now have a chart. You can now have a chart in your clinic. See, if the height is this is the weight.
This one will be this.
Do you get it? Do you get the picture, sir?
I get that concept, yes.
Yes. So the R square is just for you, is to tell you that it's fit. So it can
How useful.
very well. But the prediction is not the one doing the prediction. It is still the B, your regression coefficient, and A, you're going to use to put into the equation to do it for you. Don't worry, this question you raise now, there's one lady's work, I will run it. And after we run this, I will run it, you'll see. Because that one, she did this peak expiratory flow rate. I think the lady, you were not here. The lady joined us in one of the something. You were not part of those.
I think I remember.
Yes, that lady is in UK now. She's doing MPH in UK. The lady is in what do I call it? FITA in Ebonyi. So I analyzed a pediatrician. He has passed down. So she was doing this peak expiratory flow rate among secondary school. We now discover what are those factors. We now discover that height was a major factor, number one factor. Height, sex, even before weight. Height is number one for peak expiratory flow rate. So I'm not surprised also this issue of dead space now relating to height. I'm not surprised. So you discover most of the pulmonary function. Some is like they have relationship with height.
Height.
Yes, pulmonary function have relationship with height. So we predict, and we now have nomogram, which I did. I will even show you. Okay, let somebody first of all share. Let's share the death space and death rate. I will go and refer to that one, sir. Later, we'll do it.
Okay.
Okay, Jane, you want to do that?
You know what? Anybody, whosoever can share fast. So that's just it. So that we can move forward. We can move fast before. Whosoever can share a particular file. Death rate. I even have it here. I've opened it, but I just want you to. Okay, let me do my own. I have it here. Let me just share it.
No, sir, Jane has shared this already, sir.
Yeah, okay, that's the one. Oh, that is our own. Okay. Yes, I thought maybe it's showing my own. Okay.
No, it's her own.
Okay. I want you to, if you look at it, you see there are death rates, doctor availability, hospital availability, annual per capita income, population density. Death rate is the outcome measure here. So let's just do simple regression for each of them first before we do multiple. So go to analyze. I say what happened to the AC? We are up to analyze, regression.
Move on.
Linear. Now move death rate as dependent. Then let's check. Let's start with doctor availability as independent. Click OK. Let's be looking at click OK. Let's be looking at the R square. Click OK and share the results. Click OK and share the results.
Okay, we can't see my results.
No, we have not seen. You may
not yet.
Stop sharing and I share the result now. Yes.
Okay. Can you see the result now?
Yes, you can see. If you look great now, you see the R square is very small, 1.3%. Can you see?
Is it up? No.
Yes.
0.01.
Would that
0.01.
0.01 is the correlation. R
square okay.
1.3%.
It's 1.3%.
What did you say, Ugo?
No, I was actually asking, would that now be 1.3%? But you've answered
that's
it
already. It's 0.013, yeah, that's 1.3%.
Availability,
it makes no meaning.
So 1.3.
Can you scrub, Jen? Can you scrub? Let's see the beta coefficient.
That one doesn't have meaning, sir. You don't even need to bother yourself about that. It will give you something. Doesn't matter. But if you go and predict, it will be far from the value set. So it doesn't really matter. Let's run this second one. Go now. Just go to analyze straight there now. Analyze and let's do the second one. The second factor. Regression, linear. Remove doctor availability and now remove doctor availability and put hospital availability.
Okay.
Yes. So the thing came stop by itself. Is it you that on share?
No,
No, you don't need to unshare because he's showing it now. If you access it through, you're already in the result view. You access the analysis through result view. It will just be showing it a yes. So hospital availability is 0, is
this one is worse.
Yeah.
This is worse.
Okay, 1.2. Okay, go and analyze again. Linear. Remove hospital availability and put annual per capita income. Is 3%. This one is better. Annual
a little
per capita.
They don't make.
If income, but if you will not know. I want to show you something here. Are we following? If you look at the last table, the table on coefficient, because if you go and do correlation of annual per capita income and death rate, is opposite, is negative correlation. As the income increases, the death rate decreases. So it's going to be negative. But in your R square here, it will not show you negative as R. The one you go to know negative is the regression coefficient. Look at it, is minus
0.1.
Yes, that minus shows that as the per capita increases, the death rate decreases because
death rate decreases.
Yeah, exactly. It is the one that will show the relationship. I don't know if you understand me now. The minus is not the minus of the constant, it's the minus of that regression, that particular regression coefficient B for that particular one. Are we together? If you remember when we did for the pulmonary dead space, it was the constant was negative, but that doesn't mean. But the B was positive because the dead space increases with height. So the negative of that constant B0 has nothing to do. Has nothing. It's just telling you where the graph crosses the y-axis. Yes, I mean on the negative side. But the B, whenever it's negative, it shows that that particular exposure move in opposite direction to the outcome. That is, as that exposure increases, the outcome decreases, or as the exposure decreases, the outcome increases. But if it is positive, B is positive, it means that they go in the same direction. But if you want to know, unless you go and run the correlation, if you run the correlation, it will give you negative correlation also. But the arrow will not show you negative here. Okay, so it's only the B you can get to know it. So those are the tricky things you need to know. Okay, let's run the last one. Go to analyze the population density. Population density.
So, how many that is the slope?
So this one is 7.7%.
7%. That's the best.
Yes. 7.7% population.
That means there are other variables that are not included.
Now, you have done, if you look at it now, what we want to do now, which one, after the population density is the best one, which one give us the next one, the one that give us 3 was income. So now, want to go and do multiple now, yeah? Go to analyze again now. You want to add it, you want to add it
all of them.
Want to add it
all of them.
Not all of them at the same time. We want to do it stepwise.
What to do stepwise?
Yes.
I've always wanted to learn this thing.
Linear. Click on it.
Okay.
Now don't remove population now. Now press enter. Press enter.
All of them.
Press enter. And there's enter method sorry, press not enter. Press next. Press next. Now click on annual per capita, because that's the one that is
3%.
Yes.
Interesting. Oh wow.
Okay, click OK now.
Okay.
What it will do, can you see now? What it will do for you, can you see now? It has loaded the two. Can you see if you look at the table and say variable enter population density per capita income, annual per capita income, number 2. Can you see now? Now,
yes, sir.
If you look at it, you have done 2 models. The first one is for only the population density. The R square is 7.7. When you now add the other one, the R square increased to 9.6. So what is not telling you is that both of them account for 9.6% of the variation. Can you see?
That number 2.
What does that number 1 mean?
Number 1 mean is for the population. If you look at, we say enter. He run it separately for that one. That's why I say should enter. That's stepwise. Oh, the first one is only for is simple regression for the best, which the best we have is the population density. So now we now have population density. The second one is combination of population density and the annual per capita income. So when you now add, if you look at the other one is 7.7, you expect if you add 3 to 7.7, it should give you 10.7 now. But 10.7 because there will be some where they convert for one another, so it cannot be perfect addition. There will be some where even the population density convert for the per capita income or vice versa. That's why when you had it now, it has improved it by maybe 2. Yes, it has improved it by 1.9. In fact, it's by 1.9% it improved it. Because if it is 2, it should have been 9.7 by 1.9%. Even though when you do for you did for that per capita income, it was 3%. But it's not that 3%. When you now add it, it's not the 3% it's adding. I don't know if you understand me now. Now I want you to do something. Go back now. Go back.
Excuse me, sir.
Okay.
Excuse me, sir. Is this method called the first entry method?
No, this is not forcing. This is stepwise.
It's stepwise. Forward.
You know, let me tell you something. If when we come to logistic regression, because the interpretation differ from this one, most of the time when we do logistic, we just force everything. But when we are doing linear regression, because this R square, it gives more information. It's more useful here. It's not useful in logistic. It's odd ratio we use in that one. So we tend to do stepwise here. Don't worry. When we finish with this one, we'll run that lady's data. It's very interesting. You're going to see the way it goes. Okay. Because I will show you the result. The result is very quite interesting. Okay. Okay. Go. Now, linear. Go back to that place. Linear. Wait. What's this? Wait. Don't move anything yet. Return that annual capital income and bring doctor's availability in. I want to see. You can be. Anyway, wait. You know what? There's no way doctor availability can improve more than capital income because the value you give. Return the doctor availability. Put the capital income there. Put the return the per capita income. Now, what's this one? Is it your screen that thing? Please move the window away. Is it your screen? Remove that thing from your screen.
I'm wondering which window is asking me to move away.
You don't know which window. It has moved away. Now, press next. Press next. Press next.
Okay.
Now move doctor availability in. Because it's the one that gives us 1.3, the next best. And now analyze. Click OK. Can you see now? Can you see?
That.
So it
disappeared.
It has reduced itself. Okay, no, it's 13. No, it has increased it. Sorry. It's 13.2. That's true.
Can you see?
Oh, that's true.
Now,
Yeah.
you will see something. I was even afraid the other time. Okay, what is the improvement now? 13 point from 9.6, 30.2. What's the difference? 30.2, 9.6.
That should be about
3 point something.
Can you see? Even you notice that even the doctor availability on its own was small before, right? Was 1.3.
Yeah.
And what it has added to it is more than 1.3. That was what I wanted to do before. Okay, go back now. Analyze. I will show you. I will do something. Analyze. It has improved by 7.7, 9.6, 30.2. Linear. Now, remove that doctor. Remove that doctor. Click on previous, please. Previous. Click on that previous. Previous.
Inside the cell.
Yes, you have seen it. Remove the annual capital. That was what I wanted to do before. Annual per capita. Remove it. Put doctor availability there and run it. Want to use doctor availability? Maybe if it is next to that one, let's see. It will be more than 9.6 for us. Let's see. No, it's 8.9. It's not as good. Can you see? It's not as good as the other one. Can you see? Can you see? So it's the best. So that's the way we do stepwise. We use different method. So from now we now go back to build the model. We return that doctor availability and put that one there, and I put doctor availability, and I come and put hospital availability as the last to see if there's any improvement.
So which one will you call this type? Which stepwise is this? The forward or the backward?
It's forward. It's forward. It's forward now. If it's backward, we load everything. We begin to see which one we begin to remove.
Everything.
Okay. Now, remove doctor availability.
One by one.
Okay.
Remove doctor availability. What's happening?
So that means in the
yes, that means what?
That means in the backward, you will not need to do simple regression for each of them.
No, you can do.
Since you're loading them.
No, you can do. When you do, you'll be able to know which one you remove. You know now. You want to know the
remove. That's true.
We try the 4 of them at the same time and see?
And we can do. Let's finish this one first. We can do it. We can force everything at the same time and see. Okay. Put next. Now move the doctor availability inside. Put next. Then move the hospital availability. Okay. You see, 14. The total is 14.4. So what is telling us that the factor, these 4 factors, they account for 14.4 of variability in death rate. So we see have 86 or 85.6. 85.6 aspect that is accounted by. So that shows that whatever you are having with this factor, they are not even major. The examiner, they are not. Yes. So if somebody giving me recommendation on this, it's just useless. So if you actually want to know, the person you have to do the research and do extensive literature, what will be causing death. So when you do extensive, you bring a lot of factors, you will do the work, you may be able to bring the major factors out. So if you are able to run, let's say we run the analysis and we get over 50-something%, that shows that. And if you have one factor that gives you over 50%, there's no factor that can be better than that factor. You understand me now? There's no factor that can be better than that factor. So let's do it now and put everything at the same time, just like what Dr. Prof said.
Is that not what you
have done? You have to go back, go to remove each of them and do previous, and remove hospital, remove hospital, go to previous and remove doctor, go to previous, remove annual, yes, population density. I think that's so. Now you can just copy all of them now. Move all of them in. Control A, you can just do Control A. You do Control A, move everything. Let's see. So it will still give you. Okay. Click
okay, you don't do the next. Okay.
No, then we have forced everything instead now. Okay. If you look at it, it will still give you. Can you see? It will still give you the 14-something, but you will not know. Unless, but if you have done it one by one, you will know who contributed more. Do you get the picture now? So if you do it stepwise, you know who contributed. You'll be able to know when you are listing your factor, the most important factor, so that you know the order of importance of those factors. Okay. Any question? Because I want to share. Any question? Okay.
No.
You can stop sharing.
the questions I had by the time we ran through it and with your explanation, I think all the questions I had in mind have been answered.
Okay. Okay.
Oh,
Let
you've been answered.
okay. Let
Sorry,
me.
sir. The last one that we did, that we put everything together. Now, what's that one called? Is that one
That's
stepwise
first
again?
entry. First entry.
First.
That's first entry.
Yeah.
Okay, all right.
Then the
Yeah,
back,
that
could
one.
the backwards now be? We'll be removing it one by one.
You just begin to remove it. If as you do the first entry now, you begin to remove. You want to see which one.
So remove the first one.
If you remove the first one,
Okay.
it jack down the or something. You return it. You want to remove the one that actually
Oh.
want to remove the one that they will not contribute more. That if you remove it, it doesn't jack it down too much. That's the way to do it.
Much.
Because there are some situations when you have many factors, some of them just be giving you small dose. Why some people give you correct dose? You don't know that those are the ones
Significant dose.
that I had. So let me quickly
wow.
share this lady's that lady's work. Let me share it. You see, it's quite interesting. Let me even go to that. It's quite interesting work. And this there's this neurosurgeon also. I did his work. The same thing also was good. What's the name of this girl? Raymond.
Sorry, sir. Why you are sharing, sir? I said the first, the stepwise and the first. Is it the same thing? Is there any difference apart from the processing? We still get the same result.
What you are saying is you don't get this. You know, don't worry. By the time I do this one now, this lady, so you understand. It's because this one and the data we just did, there are limited number of variables. Variable you are dealing with. But when you have many variables, you cannot just force a Dick and Harry inside. If you force this and Harry inside, in fact, some of them will have destroyed the work set. But if by the time you begin to take it step by step or remove it, that's where you maximize it. Or you go to see. Just wait. Let me along this something so that we won't waste time. Let me also share the result I work so that you see the way it came out of this. Just a minute. Must you say where is welcome back from? Okay. Okay. Okay.
So I'm not sure. Let's just see that. I mean, let's go and do it.
Okay.
When you want it, you should go and check whether the thing is inside the.
And you didn't I ask you to do that? When he on this, I told him. He said it's not feeling. I said it's not the feeling. Make sure the thing is there. Okay, can you see? Can everybody see? Hello?
Yes.
You
Step
can
1,
see,
step 2, step 3, step 4.
can you see this work? Okay, before this one, let me even show you. Because I want us to look at, you can see this result now. This is a simple one. Are we together? Can you see?
Yeah.
This is a simple one. The arrow square, the one that gives the highest arrow square, if you look at it, is
Weight.
Is is height, 26.9. Can you
Sorry,
see?
height.
When I did each 1, 1, 1, 1, the highest R square is height, followed by weight, followed by weight, then followed by age, then followed by, can you see? If you look at but thank you. Blood, it's only blood pressure. But you will go to see something now. So I will not bother us to, okay, I will not bother us so that I won't waste time to be doing the simple, because these are the result. But the way I now come to now know, come down to height, age, second, sex, weight. Can you see? Even the systolic blood pressure you see did not come in here. You're going to see there are a lot of confounder. Can you see now? So let's just see. So let's start with the outcome measure. Then we start with height. Height, yes. Can you see it? Let me.
It's still the same table.
Can you see it? I shared the something now. I shared this. Yes. Usually, for me to know, sometimes the data I don't take. Where is that peak expiratory rate? I think that one.
There are three.
Yes, I think it's that one. So it's one. It's the one dependent variable. So height. This is the height. Yes. Let me share the results. Can you see it? Can you see the result?
Yeah.
Can you see the R square 26.9? Right? So don't worry.
This is clear.
Yes. So 26.9. Let's put weight. You will see something. Can you see weight is? Can you see 22.1, right?
Next weight.
That's weight. Sorry. Let's put age. Age is 80.9.
18.
You know, 80.9 looks smaller than 70.9, right?
The other one was 26
yes.
something.
Yes, okay. Just to confirm something. What do you say?
This one is smaller than the three.
Smaller. So what I will do something now. Okay, let me first of all put the height in, which is the something. And let's put the weight that's supposed to be the next to height, right? As the next one. So if I enter together, I don't see next. The only thing, it will not repeat the height for me separately. It will just do it as one. Yes, I'm not. But it's good to put it like so that you can be seeing the progression. So, no. Wait, what did I put?
Yeah, you're right.
I know, I'm coming.
Next.
I know, I'm putting height. I know. Mistake. It's supposed to be weight.
Oh, no.
Come on, wait.
Yeah.
Can you see what improvement has he brought? Something was 22.1. It's now 30.
It's
so
30%.
Something is 22.1, and this one is 26.9. So what is the addition? The addition is 4 point something. It's 3.7, 3.1. 3.1. Can you see? That shows that most of the thing you are seeing in the high is because of the weight. You know, if somebody averagely, somebody that is tall, we have weight. I don't know if you understand me now. Somebody that is tall, taller person will have weight also. So averagely tall person will have the weight also will be more. The only thing is that the shorter person will have more BMI. I don't know if you understand me now. The shorter person will have more BMI. We may have more BMI, but the average taller person will still may have weight more than shorter person. So it was the height that was confounding as if the weight is responsible. It's still the height that is responsible. Because most of the people that have because it's not BMI you are using the weight. I don't know if you understand me now. Now let's now use age. Let's use age now. This one just had 3.1. Let's use age instead of the something. You see what will happen. So I remove height. Let me put age instead of weight rather. You see. Can you see it improved 31.5? So age improve it more than weight. I don't know if you understand me now.
Sure. This is up to 4.
Yes. This is
4.
Yes.
4.7.
4.6 or whatever. 4.6.
Or something 4.6.
So this one improve it more. That was why you now see on that table that age was the second one. Can you see? Can you see? So it moved the 26.9 to 31.5. You'll be surprised also if let's add after we have added weight, the age, let's add the weight. Also let's add the sex. You discover that even sex is still better, male sex, because I coded the sex because the peak expiration flow is higher in male than female. So I now coded the male 1 and female 0. This is a form of point by serial correlation now, if you are correlating them. So let's see. Okay, let's even see for let's see condition of sex now. Regression. So age is the second one. Next, let's now put weight to see from that 31.5. Let's see what weight we had to it. Since the weight now, we want to see what we had to that 30.1. Can you see? What did weight add to 32.8? What is different? You just added
not much.
He added 1.3.
Not much.
So it's 1. He added 1.3 to it.
There's not much improvement.
So let's now do it and add sex. You see what sex we have to do. So, sorry, I want to click logistics. So instead of it, sex, you will not use sex the way you put it to. I've coded it. I have to make sex. So, can you see? What does it give you? It's jack it to 36.1. Can you see? So even here I stop also. When I was doing it, I have to even remove age from the first something and tried sex. But the weight, the sex does not contribute like weight, age. So after height is age, then followed by sex before the weight. So all those other ones were tried also, or even the systolic blood pressure that appear to see as if it's significant is lie. The systolic blood pressure you see, it doesn't contribute much to it. So at the end of the day, the theory that improve it appreciably is up to 38.4. More yes is height, age, sex, and weight. So those are the ones we now put in the model equation. And you see, since sex is categorical, so we now have the equation for male and female. And you see now, so height, age, weight. Height, age, weight for male and female. This is the equation. But when we run it, the coefficient, the beta, whatever we get in our beta, now feed it into the equation. But if you still look at it, everything, all these four, they only account for 38. But the only thing there is that sometimes also the remaining one, you may be saying the remaining 60-something%, there may not be one major thing that account for it. It may be thousands of things, hundreds of things that just contribute small. I don't know if you understand me now. So in some situations, it's not as if maybe if you are able to explain 30-something remains 60, that maybe there is a factor, one factor I know. That 60 say it may be thousands of factors, small that contribute bit to that thing. So any question concerning this?
Yes, I was not here yesterday, so I'm interested in yes.
It's new in data.
Hello?
Yes,
Can you hear me?
Go on, sir.
I wasn't here yesterday, so you need to clarify how you can use the regression coefficient to predict. That aspect I'm not clear at all.
Even that
please,
before we left, you left, and we have discussed it again.
Hello, sir.
Okay, go on, sir. Go on, sir. Yes, sir. We'll explain it. No problem. Go on, sir. Go on.
Please, sir, can you explain the F ratio there? The F ratio.
Age ratio.
The F
ratio. That's the ANOVA now.
No, yes, that's the ANOVA. That's the ANOVA. The F ratio. The F ratio in this result.
Yes, sir.
Is the ANOVA there?
Yes.
Is the ANOVA
the F ratio here is okay.
The regression.
Yeah, let me just, don't worry. Let me just go to that data set now so that you will be clear there. Yes, look at the
C directly.
Yes, C directly. Look at the F ratio. Now, the model summary. This sum of square. Yes, I mean, are we together, sir? You know, when you first of all run the what do I call it? It will give you the total, because we are okay. Yes, this is what the ANOVA. Sorry. Look at it. Now, this F ratio, you can see for each category now. What this one is telling you is that the regression, as you are putting more increasing something in the model, it is increasing. Look at this, it's increasing the variability out of the total variability. Because the total variation, total sum of square is 6703086.211. That's the total. So the first one, the first variable, which is the height, explain 183,044 point something of it. When you added the other one, look at what is it. It has jacked it up to about, can you see? Because this one now is around the total something, if you are to put, is 6.7 million. So this one accounted for 1.8. Then when you added, it accounts for 2.something million. Variation. Then when you now add the third one, it accounts for 2.4. So the F ratio now, the F ratio is now, you now calculate this sum of square. That is total sum of square. You want to know the variance, you now divide by the degree of freedom. The degree of freedom is now 66. Because the sample size of this person is very large. His sample size is over this. Yes, the sample size is 9,600. 9,700. Yes, the total sample size is 9,700. So when you now divide it by the degree of freedom, it gives you this variance. Then the variance for this is the variance rather. You know, the variance for the residual, if you divide the one that cannot be explained, is this 4 million, you divide by their own degree of freedom, it gives you this. So the variance for the residual is this 4,432, and the variance for the model you are building with the three of them is 807,052. So when you now F ratio is variance for the regression over the variance. This is the variance the regression can explain over the residual, the error, the variance the regression cannot explain. So you want now, to see, is this thing good? Yes. If you now divide the variance it can explain by the one it cannot explain, is 182 times. That's the F ratio. So it's telling you that what it can explain is 182 times more than the one it cannot explain. That's why it's significant. And so the F ratio together with the R square, they are measure of goodness of fit. They just explain that, oh, this model is good. Is it clear? Is it clear, sir?
Yes, it's clear, sir.
Yes.
Thank you, sir. Yes.
I even look at it, those are the things we explain also under the at the initial. Actually, if you conceptualize very well, if you have been following on this ANOVA, because we discussed this the variance between variance with it. So F is a comparison of variance. Yeah, you are dividing a variance by a variance. That's why I call it F ratio. It's a ratio. So now, what I want us to do now, I want us to, who has that ANOVA data, libido? Somebody should, is it libido or Viagra? Viagra. Somebody should share it. Somebody share so that we look at, we run ANOVA and run use to run. There's a dummy there so that you see the way they create dummy. Because there's a dummy in that that data set. Who has it? Somebody should share.
What about the question? What about my concern?
What's your concern?
My concern is that I don't know, as I was not here yesterday, I don't know how to use the regression coefficient to predict anything.
Okay. Sorry,
Yes.
I thought I forgot what you said. Okay, it's very, where will I start from? Because that is very plain. We explained it. Okay, let me just go back.
I wasn't around. I was not there.
We explained the same thing today. We explained the same thing today. Don't worry. I will explain.
Okay. Okay.
Why is this thing not? Wilderness and Lambert. Yes. So when we're talking of this thing, you were not following. Did you follow it? Follow this, all this slope.
Yeah, I followed the slope.
Yes. You understand up to this place?
Yes, I understand.
That is how to predict it. What we are saying is that y is your outcome variable. Y is your outcome variable. For example, this one just did for this listener, expiratory flow rate will be y. BO is the intercept where the graph cross y-axis.
Constant.
The one that you are seeing A. That's the BO. In the equation, they usually write it BO instead of writing A. And that is, it makes sense because in the I will show you in the expresses is beta also, as is a form of regression coefficient, but 0, they call it B0. Now, B1, this equation is for simple regression, that is only one variable. So B1 x1. This is the value of the variable x. This is the regression coefficient for this. We want to calculate
coefficient.
This is the equation. So all we need to do now is to get to know B0 and B1. So if somebody now give me, let's say, height.
What is B1?
X.
What is B1?
B1 is the regression coefficient for the variable.
Okay.
For the variable, for the x, for the independent variable. Like in this case, the height. Now that we are looking at the explosive flow, peak explosive flow rate and height. Peak explosive flow rate is y, is the outcome variable. X is the height. So the B1 is the regression coefficient, is the change in the value of y per unit change in the value of x. Is the slope of this graph, is the slope of this graph, that is dy dx. That is this change divided by per unit change in x. That is when y x move from this point to this point, y move from this point to this point. That change over the y is the slope. If the slope is very steep now, you're going to see that that b will be much more than what it is. If the slope is flatter, this b will be smaller. So the more the slope, the more change in b, in y per unit change in x. Is it clear?
It's clear.
The a is where is the constant, and it is where y, the value of y when x is equal to 0, because when the graph cross y, if you trace it back to the origin, the value
of x will be 0.
Yeah, that is when the independent variable is not there at all. Y still has value. That's why they call it.
Y still has a value.
And that's why they call it constant. That is either the exposure is there, or not. The Y has a value. That's why they call it constant. And that is the B0, that equation. That's the B0. By is the B, is the regression coefficient. Simple. If you now have multiple, when you are having more variables involved, so y is still y. Big expressive rate. B0 is still the constant. But because we don't have many x, this is B1 for S1. This is B2 for the second one. If there are many like that, they will have, each of them will have their own regression coefficient. Now, this one is just adding flavor. This one I didn't account for, this equation does not account for the residual. Because it's not everything, even with all these constants, it's not everything that you can still predict. So there will be error. That one is accounted for here. That is why, can you see predicted output is equal to B0. If you get B0 and B1, these are the coefficients. This is for constant, this is for the variable. Exposure variable X. And this is for single variable. This is for simple regression. This is the error. This is multiple regression. And see the Y, this 0, this Y. Then this is to as many, that's why they could be as many variables. If they are up to 10, it will be B2, B2S2.
Blah, 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 blah.
Up to like that. So when you plot the graph, the issue is that most of the time, or what will happen is that all of them cannot be, the value you see is not, you cannot actually be, all of them cannot be on a straight line. Even though you're having a straight line, all of them cannot be, you have a line, you're going to see there will be different in their value from the, all of them will not be on the line. So now, these are the data points, what you observe, this is the line. So now, if you have to draw the line, I think I've talked about the method of least square. The method of least square, the line, look at the line now. The line, the difference between each of the points and the line, look at this. Where the point is the observed value, what you observe in your data set, that is where X and Y meet for a particular value, that is those are the dot. Then the predicted value by the line is where the particular where that point join that line. This is the predicted value for this point now. But this is the observed value. So the difference is the error. Error is X, Y, Y, all over Y, this. That is the difference between these two is the error. So the one that are below the line, their error is negative. The one that are above the line, the error is positive. If you square them, it gives you a value. So the best line, if let's say you draw different line now, you draw different line for this thing now. If you square the deviation, that is the difference, the error, you square it, and now add it together. The one that gives you the smallest, that is the best line, because that is the one that marks it, that gives you the shortest distance from each of them, averagely from the line. That is the line of best fit. That line of best fit is gotten through the method of least square. That is, when you square them, the one that give you the least, when you add it together, that give you the least value. That's the closest, that's the line that is closer to all the points averagely. Does it make sense?
Yes.
So, now, sir, if I wasn't the one that asked the question, I think I benefited from it. I want to ask a question, sir, before you move on.
Okay.
This predicted value, the predicted value we're talking about, I see the exposure here as our observed value, and then I see the predicted value. So how do...
I'm not hearing you again. No. How what? Hello?
Maybe how do you know what the predicted value is? Okay, she's back.
It's not a matter of you don't even know it's the graph that know. That's what we're telling you. If the line is plotted, where the line perpendicular, look at it now. The observed value is where the point is. So where the distance between that one, just draw a perpendicular line to join the. So at that point, that is the predicted value. That's what the line predicts. So as in
when using just a minute, okay.
Okay, so what is the value? Okay, now we don't have any.
You don't need to calculate. You don't need to. You see, that's this. You don't need to. Okay, you don't need to.
Okay.
You don't need to calculate it. Yeah.
Okay, now when you use SPSS to get the value of P,
yes.
In the SPSS, this graph is not there. This the line that fits best is not there with you. So how do you?
If you want to
calculate?
If you look at it, both equation and graph, they are all modeling. They are showing you the same thing. Equation will show you formula. The other one will show you picture. Okay. There is mathematical equation that will solve it for you.
Okay, so I should just put those values in that formula and do calculation.
Yes, now. Okay, even the B you are talking of, look at it now. Look at it. The B we calculate.
I have seen the formula. I've seen the formula.
Yes,
I have seen the formula.
One after the other, please. One person per time, please.
I'm saying that I drew a model like this, which I could not defend. The model looks so beautiful with everything that is here, but I couldn't defend it.
Oh, where?
That was last year's story for another day.
It's because maybe somebody did the model for you, don't know, and you don't understand the logic behind it. So look at it.
I didn't understand the logic behind the model.
Yes. Even though we have already calculated, even without the something, we calculated it out now. Look at this thing. I use this to to generate this one. We calculated the thing out now. Look at it. We calculated the correlation coefficient here and regression coefficient. We put the value. Look at it. Look at it. Okay. You understand now? We say the B. We have already said that the correlation is covariance over standard deviation of the X and Y. Covariance of X and Y over the standard deviation of X and Y. While regression coefficient is covariance of X and Y over the variance of X. Because what is the B, the slope, is change in X in Y per unit change in X. And change in X on Y, the part of Y that's changed is the one that's changed together with X. That is covariance. So can you see that B is covariance of X and Y? This one is the covariance now. Divided by the variance. This is variance of X. That's the formula for variance. X minus X bar square over N minus 1. When you now change the times now, you change the something. In mathematics now, this one would become, if you want to change this negative to division to times, you change numerator to denominator. So you see N minus 1 cancel N minus 1 out here. It will now become this, and this is the formula for the regression. If we put in the information now, look at it, we get the information here. Okay. This and this. We put in the information, it gives us And when you run it, even with the computer, it's not the same thing it gave us. Do you get the vision now? So sometimes
Yes.
it's just like when you calculator, you press. How did the calculator get the answer? The calculator get the answer because they have already programmed the mathematics. If you bring your pencil also and solve it, you get the same answer. So the computer is what they program inside. I don't know if you understand me now. So
Yes,
all this explanation is for you to have a mental picture of it. All this explanation is for you to have a mental picture of it.
The logic behind
Thank you.
what the machine
Okay, let's move forward.
So
let's move forward.
So it's the same thing here. We just say, okay, look at the line now. From this, the slope now, you're able to get the regression V1, and VO is 0 is the intercept. So I now explain it here. The question Professor Togiden was asking, that is the explanation here. If, you know, if people that have been with us for our NOVA class, we quickly understand this space, because we have been saying that ANOVA and regression is the same. And this is where you see that they are the same. You understand me now? So look at the question, Prof, are you there? The question was asking about that.
Yes, I'm here, sir.
F ratio. F ratio, you know, we say that is variance that can be explained by the model over the variance that cannot be explained by the model. You understand me now? It's the same thing now, ANOVA. Variance between over variance within. Because the between, when you have in ANOVA, when you have 3 groups or 4 groups, that is the model. The group is the model. Now, the variance that can be explained, the difference between that, the mean of each group and the grand mean, that is the model variance, divided by the variance within each of the group. That is the one that cannot be explained by the model. So it's the same logic here. So if you look at it, the total variance is gotten from, look at the mean of y. They just mark a place, a horizontal line representing the mean of y. If you look at this same point, when you look at it from the mean of y, they are averagely, they are far, far, far from the line than the regression line. So the mean is the crudest model. The mean is very crude. If you use the mean to predict, in fact, you are just wasting time. I gave an example of somebody that, you know, send a friend went to UK. Okay, let me buy jersey for inter-sport for my nursery and primary school student for their inter-sport. Buy about 150. That one I say, okay. Now come, I'm there now. How? What is the age? They are asking what is the average age of your student. You now call a teacher. What is the average age? They also say 7 years. 7 years is just the average. Some are less than 7 years, some are more than 7 years. So most of the jersey they brought for 7 years, 150. That is how poor mean is. Because mean assume that all of them are the same. So I think I explained it anyway. We are not the same. It's just as we are here in the class now. Someone can just calculate the mean age. You calculate the mean age. What you did is to add all the ages together and now divide by the number of people. That is the mean age. What you are telling on him is that you have gathered all the ages together. You have shared it equally among everybody, assuming everybody have the same age. Or maybe they now brought money for us now. They say we should share. We should share 1 million. And we are 10 of us. People just say, 100,000. Believing that we are all equal. That is the assumption. But the prof can decide to take 600,000 or 400,000 from it. And the next prof will take 300,000. So the remaining, maybe 8 people may have to be dealing with 200,000. And that is how life is, because we are not all equal. So the mean assumes that everybody is equal as per certain item you are measuring, variable you are measuring. So that is why the mean is there. But each value are so far from the mean averagely. Some are close, but if you look averagely. But when you develop, so the variability you are going to explain, the total variability that's to be explained, is what is presented by the mean. Because the mean, how do you do that? If you remove the mean from each value and square it, it gives you the total sum of square. That is why SST. See, SST uses the difference between the observed data and the mean value of Y. That is the one you see. You are seeing T in the regression something I will show you. Total sum of squares. That is the, so that total sum of square is the mean of Y. The deviation, the difference between the mean of Y and each value that give you that way. You can go and try it. In the something. If we calculate the mean expiratory flow rate now, and now remove each value from the mean and square it, that is the value that will give you. That thing you see there, that's what will give you. The expression, you see the expression there. Now, if by the time you now do your regression line, you will see that they are closer to the line, but it's not perfect. Not all of them are on the line. There are error. You cannot predict all of them completely. So there is error in the prediction. Now you want to know how good is this something. For you to know how good, this is the total variability. Then this is the one that presents with some error in capturing it. So it's just like this is a total problem. This is the problem unsolved. So the problem solved will be the total problem and the problem unsolved. That is why the variability explained by your model now will be this total variability minus the residual. The residual SSR uses sum of square residual, uses the difference between the observed data and the regression line. So when you now overlap them, you remove this from the total. It gives you the sum of square model, which is SSM, using the difference between the mean value of Y and the regression line. That is the difference you get from the total and the regression line. That is what. So what is telling you is that the improvement the regression has made is the difference between the error and the one presented by the mean, which is the total sum of square. And that is, so in trying to see how good it is now, that's okay. If you now divide the sum of square model, the improvement over the error. If you put improvement over error, that is the F ratio. It's telling you how much more that the model is good than is not good. What is able to accomplish and what is not able to accomplish is the error. When you do that, divide, you make what is able to accomplish as the numerator and the error and denominator. If the what is accomplished far greater, it will be greater than 1. So in this situation now, you will see it's around 132 times greater or more than that. It means that the model is good. That's the explanation of the F ratio. And the R square is the what proportion of the total variability can the model explain. Can you see now? So the R square now is this SSM divided by total. While the F ratio is SSM divided by the error. Can you see? So the model, sum of square model divided by the total sum of square is the R square. Is the R square coefficient of determination. While the sum of square model divided by the sum of square residual, which is the error, that is the F ratio. Those are the two things that measure the goodness of fit of the model. So if they are big enough, that shows that the model is good. Then you can now begin to use your B and A to predict. We see the case for a case of pulmonary dead space. The R square is around 71%. So if you look at the prediction we made, it's around 71% also. If let's say we have other factor that came in, maybe we have other factor that we add it to that height now for the dead space, and we're able to account for 90% or 99% or 97%. You can now predict the value up to, with that model, you predict up to 90-something%. So is it clear now? Is it clear? Any other question? Any other question? Dr. Ikobo. Dr. Ikobo.
Thank you, Prof, for sort of
No, I'm okay.
You're okay now, right?
I'm okay.
Yes. So you can see how he used to predict now. So who is sharing that Viagra? That's the last one, so that we just leave. Who is sharing that Viagra? So that we just see. Who is sharing the Viagra? Okay, maybe I should share my own there.
Okay, I have it open.
You have it to share it. Is that opening?
Oh, it has opened.
Unable to share.
Okay.
Can you see it?
Yes. Yes. Okay. Go to the data editor window. Data view. Data view. Click on the data view. You will see that the dose is the exposure, the libido is the outcome. We have dummy 1, dummy 2. So now, because of the regression, that's why I created the dummy. If you look at me, when we're doing ANOVA, we didn't use that dummy. Now, how many categories of do we have for that ANOVA? How many categories of the dose? I want you to respond. I want people to respond. I want you to be sure that you understand. How many categories?
I think there are up to 3 doses.
There were three categories.
Yes. And you can see now 1, 2, 3. If you go to, you click on view now and click, you go to see this one will be placebo. 1 is placebo, 2 is low dose, 3 is high dose. There are 3 categories. Now, whenever you have 3 categories, you want to create dummy, you create
3.
Yes,
3 categories.
3 categories. You now create a dummy, 1 less the number of categories. So you are creating 2 dummies. I don't know if you understand now. So you are holding 1 category constant, you are creating 2 dummy for the other 2 categories. Does it make sense? That's why you can see 2 dummies here. And when you look at it, we hold the placebo constant and created dummy 1, dummy 2, dummy 1 for low dose, dummy 2 for low dose, for high dose. So in creating the dummy 1 for for low dose, you see it's only low dose we mark as 1, the rest is 0 because dummy is 1 and 0, 1 and 0. Can you see now? If you look at the 3, look at the dummy 1 now. For number 1 to 5 that are placebo, there is 0. Because that dummy is created for low dose. The number 2, number 6 to 10, which is category 2, which are low dose. For dummy 1, they are 1. Why the other one? When you come to dummy 2, which is for high dose, it's only the high dose that is 1. The rest are 0. Does it make sense now? The implication of it is that for dummy 1, placebo.
Sorry, sir.
Please explain it again. That
yes, because
position.
I missed it. Yeah, I didn't get it.
When you are creating dummy,
that is dummy 1, dummy 2.
Yes, you are creating. You are. If there are 3 categories, you will hold 1 category constant and create dummy for the 2 other categories. If let's say there are 2 categories, if it's male and female now, we only create dummy for 1. You can decide to say 1 for male, 0 female. That's your 1 dummy because there are 2 categories. If it is yes or no, you can say you create dummy 1 for yes, 0 for no. But if there are 4 categories, we're going to create 3 dummy. But there are 3 categories, we create 2 dummy. You hold 1 constant. That one you hold constant is 0, 0 you put there. So what I was saying that for everything for the 2 dummy is 0, 0.
Excuse me, I have a question, sir.
Yes.
This what will determine the one that you hold constant? Why can't we hold the high dose constant? Why not the low dose? Why
Yes,
are we holding the placebo constant?
yes, yes. You can hold in situation. It depends. If you okay, were you part of yes, you were part of the ANOVA now. You know,
Sure.
yes, you know that the way what you do depends on your hypothesis. Yes, I mean now.
Okay.
In this case
Okay.
now, if you want to do the regression now, we expect that the outcome, because the outcome is libido, the expectation is that, or expectation or the hypothesis, which is based on the expectation, is that the high dose and the one low dose
Higher dose.
a higher dose should give us more libido. I don't know if you understand me now.
Yes, sir. It's okay, sir.
Higher dose should give libido. So placebo should not even give us much performance. So the middle performance should be the low dose, while the high performance should be the high dose. Is that not the expectation? So in that case, if you want to now say by how much you want to know which one is higher, you expect the libido among the high dose to be higher, followed by the low dose then to be more than this. So that's why we hold the placebo constant to really know how many times the libido will be higher among the low dose, higher than the placebo. Then will be higher among the high dose than the placebo. Does it make sense now? So in some situation, if it's something that else you feel that should be less with the high dose, we can hold the high dose constant. And now, if you remember, when we're talking about contrast, that is there are different type of contrasts. You remember, in some situation, you can decide to hold the high dose constant, and now you can. Even like if we are doing analysis, we see that look at the regression we did, the last one for that lady, the one for peak expressive flow rate. Because when I was cross-tabulating, I already knew, or when I was doing the mean, I discovered that the expressive flow rate is higher among the male than female. You understand now? So when I was creating the dummy for sex now, I make male 1, female 0. If I make female 1, male 0, it gives me the same result, but the interpretation would be upside down. I don't know if you understand me now. It will be upside down. So it will be what it will, the regression coefficient will be, it's the same value, but it will be negative. I don't know if you understand now. It will give exactly the same result, but you now have negative sign. I don't know because one, yes, opposite direction, because the one I have already put forward.
Oh, sir, can you take that again, sir?
I said that if for that lady's owner, no, I coded the male 1 because I created a dummy for the sex. For you to do sex, I have to create dummy.
Yes.
Then I decided to make male 1, female 0, because I've already known from the result that the peak expressive flow rate, what I mentioned, is higher among the male than female. Okay. If I created it otherwise, if I put female, knowing that the female is lower, I put male 1 and male 1, the result will come out the same thing, the same regression coefficient, but it will be negative. It will give you minus. But it will not change anything, you just give me 1 minus. Do you get it now? So sometimes, if it is a logistic regression you are doing, if you decide to create 1 for the one that will have less of the attribute, what will happen now? The odd ratio will be less than 1. But if you create the 1 for the one that are more likely to have the attribute, because in that case you are saying how many times is it more likely to have it. So it will give you odd ratio that is greater than 1. So the odd ratio that is greater than 1 is easier to interpret. You get a picture, but it's the same result. So how is based on experience? You do it, you know. Now, this one now, we are creating 2 dummies for 3 categories. Now, the dummy we are making placebo constant and creating 1 dummy for low dose and 2nd dummy for high dose. Now, the dummy for anyone, that particular category will be 1. Anything other thing will be 0. Look at that number 1 is for low dose. All the numbers 6 to 10 that are low dose will create 1. the rest 0.
Even the high one
Yes,
will be
0.
0.
Because
And
it's
the
only
placebo
that
will be
dummy
0.
exactly. Yes.
Okay, I now
That dummy
understand.
is
Okay.
for low dose. So anything low dose you want, any other thing that is not low dose is 0.
0.
So
Okay.
the dummy 2 for high dose. Anything high dose is 1, any other thing 0.
1. Every other is 0.
The
Okay.
implication of that is that you have 1 for under the dummy 1, low dose 1. Under the dummy 2, high dose 1. Whichever, either the both of them, the placebo is 0 because it's the reference. You get the picture? It's the one you hold constant. So it's the same thing. Either you are doing logistic or linear or whatever. So anytime you are using categorical variable, you create it on. The only thing.
The one you okay.
Go on. What? Ask your question.
No, continue. No, continue.
Excuse me. Assuming the samples that you are dealing with are large enough for you to rely on maybe SPSS, is there a command, maybe on transformation, that you can give to just create the dummy at once instead of you using hand to calculate up to maybe 100 variables?
No, it's not that now. Of course, even that lady's own, that one that we are dealing with 970. That's what I did now. There's a way to do it.
You use manually.
It's not manually. I use the SPSS. I just say for May, select the way we do select now. Select May. This one is May. When I select it, you go and mark it as all those May 1, the other one 0. I just go and change it. Let me show you because I have not. Okay, if I have to show you, maybe later, not now, because if I have to do that, I have to stop sharing. Let's run one. I will show you this thing. So no, it's even the same thing. Jane, go to variable view. Go to variable view.
Okay, sir. So while she's moving, the one that we hold constant.
Click on the value of Okay, I didn't label it. Don't worry. Go on. What did you say?
I said the one that we often hold constant. Is that the 0 or the 1? The one you see, because you said something about reference, and I know it should be the same thing as the one you want to hold constant.
Hold constant is usually 0 now. The reference is a 0. Even if it's logistic, the one you are holding constant is the reference 0.
Okay.
If you look at in your logistic regression, all those ones we put 1 on those one that we hold constant 1. We are
yes.
So
the remaining ones were 0.
Doesn't mean that when we are creating the something, is the one we mark 0. Even though we mark it 1. Do you get the picture now? Is the one we mark 0. It's the one we create 0 dummy for. Like now, if I can make a female 0, male 1.
Yes.
The reference is female. So on the when we are doing the regression, under the female, I just put 1 because that is the reference. Even though it's the one that marks 0, under the table, it means that what that one just means that how many times is it more likely to have bias than say is 1?
More than female. Okay, because female will be lower.
That's why, yes, that's why you put it at 1.
Okay, I now understand. Okay.
Go to analyze. Go to analyze now. When the first one run and over, we now run regression. Go to compare means. That's compare means. One way and over. Okay, libido, dependent list. Move libido as dependent list. Then dose as the factor. Okay, click OK. And share the result with us. Share the result. So that's the table down, and over. Can you see? If you see, this table is the same thing as you have seen with regression. Sum or square, the same thing. The only thing is that instead of writing regression, it's called between groups. within groups. Instead of writing regression, instead of writing residual, he wrote between groups.
Within.
Look at the F, 5.119. Look at the p-value, 0.025. Look at all these mean square, 10 point, all those. Look at the degree of freedom, 2, 12, 14. Now, go back. Let's do the regression now. Go to analyze. Analyze. Go to regression. Linear. Linear. Okay. Dependent list, libido. Dependent, libido. Independent, that those two domains, low dose and versus, just copy those two domains. Those are the, so you are not using the dose. Because this is, yes. Click OK. Click OK. So look at the ANOVA table. Is it not the same thing? Look at the ANOVA table now. Here. Can you see?
It's the same ANOVA.
It's the same ANOVA. Can you see? Sum of square. Look at everything. The F. Look at the same.
Look at that.
Look at the only difference that here regression. There they wrote between groups. Here residual. They wrote within groups. That's all. That's the only difference. Or you want to go and copy both of them on a to see.
Now I was just trying to see the ANOVA again. That's
yeah,
first one.
Scroll up small.
So I'll just look at it. No, it's still up.
Yeah, look at it. Look at it.
Oh, look at that. So between groups is 20. Okay. So let's go down.
Hello.
Yes, sir.
I was thinking that in the SPSS, so on the SPSS, there is no place for logistic regression. You will still use linear regression.
What are you saying? We are not doing logistic regression. There's a place then. This is not logistic. We are doing linear regression. Is the logistic regression is another training. It's different from this now.
Okay, this one is we are still on linear regression.
Yes, now.
Okay.
Because we are having the dummy category. So you see, what you are missing is this. In linear regression, the outcome is continuous. The exposure, your factor can be anything. It can be continuous, it can be categorical, it can be anything. But whenever you are using categorical for any regression, you must create
you have to convert it. Yeah,
okay. Even when you are I thought we are on logistic. Okay.
No. Even when you want to do logistic now, the outcome has to be categorical. The categorical variable, you have to create a dummy for it.
Okay.
So I think we are true because.
Hello, sir.
Yes, sir.
No, sir. I assume if we had more than one predictor variable, let's say we had,
I can't hear you. Is it my
those and
your network is not good. I'm not hearing you very well.
Maybe set.
Your network is not good. We can't hear you.
No, some other thing. How would we have a hand? You understand? Two predictor variables.
Your DC was breaking. We didn't hear you. Maybe you send test. Is it chat? Send chat.
Hello.
Hello, sir.
Hello. Just an aside. Can we exponentiate the beta coefficient? Can we exponentiate it?
No, you don't need to. This one there, you don't explain. We only do that in logistic regression. We'll do that when we want to treat logistic. That's why we do exponent, and that is odd ratio. When you calculate the exponential of the beta, it becomes odd ratio. So when we get to logistic regression,
in this linear,
you don't do that.
So in this linear, we cannot exponentiate the B coefficient.
Why will you exponentiate it? It doesn't make meaning to exponentiate it because the beta coefficient is doesn't make meaning in logistic regression. That's why they do the exponentiation to calculate the exponential to calculate odd ratio. Okay, we will have to create more dummy table if we have more. No, that Dr. Professor Tokedem.
Yes, sir.
Yes, no, it's not like that. The issue is that you have to create more dummy if the category of the categorical variable are more. Like now, if there are 4 categories now, we are going to create 3 dummy for it.
3.
So whether we are going to create dummy for more variable depends on whether the variable is categorical or not. If the variable they are continuous, you don't need to. You are not creating dummy for them. If they are quantitative, it is when they are categorical you now create dummy for them. I don't know if you understand me now. If you look at the one we did. Look at the one we did for that girl. Is among all the variables we put it only the sex that is categorical. That was the only one we created dummy for. Look at the one we're doing for death rate. All of them are quantitative, so there's no need to create category dummy. When you need any particular variable you want to come in and it's categorical, you must create dummy. And the number of dummy you create will be number for that particular variable would be number of category.
We had sex.
Yeah.
What if we had like sex in addition to the dose?
Yes, we create dummy. We have to create dummy for the sex. Yes. But this one is only one sex, so the performance we are looking at is only one sex. It's only one sex that use Viagra. But if we have another variable that is categorical, like ethnicity, like a race, yes, you now, since the category, we create dummy for it also. Does it make sense? So you can stop sharing. Stop sharing. Hello? Hello?
One has gone.
Jane, stop sharing.
Hello?
No, that's
Hello?
what I can hear you. No, that's what's happening. Yes, yes. It's like this. Yes.
You went off.
Hello, can you hear me?
Yeah.
Yes. Oh, we have covered our timetable.
I think so. We are getting fatigued.
Okay.
We are
true. We are true. We are true.
Thank you, sir. Thank you, sir.
Okay, welcome. So we have learned something now.
Yes, so.
This one is more interesting than all the differential we've been talking about.
Yes, I told you that the regression is quite interesting. It's quite interesting.
Yes, I missed part of the regression. I'll join you next week, sir.
What do you say?
I said I missed some part of it today, so I'll join you next week, especially on Sunday.
No problem. No problem.
Just for the regression.
No problem. You can even join from the beginning. Dr. Babagana.
Are we totally done with regression?
What do you say?
Are we totally done with regression? We have not done logistics.
Linear now.
Okay, linear. Okay.
It's linear now.
Logistic is another model.
Correlation and linear regression. Logistic regression together with stratified analysis. They are different things.
Okay.
So what you can you all of you can come pro bono if you want to for next week. But make sure you bring somebody to come and subscribe. Bring somebody, at least one person to subscribe for them, and then you come free. You understand me now?
Okay.
So invite somebody. Okay, let me stop the